Hello, everybody. Benefits of being able to make a video is that we can now finish the lesson online. Okay, working on lesson 22 of unit 2, distribution shapes. We did most of the lesson in class. We talked about if you draw a frequency polygon or histogram. All right, we made histograms right here. You look at the overall general shape. The first part of your worksheet packet is to make a frequency polygon or histogram if you'd like, and tell me what the general shape is. We have uniform distributions here, which it doesn't look exactly uniform, but it's close enough. Bell-shaped or symmetrical. We've also gone over, talked about distributions that are skewed to the left or skewed to the right. Bimodal, if there's two humps in your histogram or frequency polygon, it's bimodal. If there's multiple humps, it's multimodal. That's the first part of your worksheet packet homework. Actually, the second part. The first part deals with a question like example 3. This is the one question we did not do. Warning, there will be a test question like this. It is probably algebraically the easiest question on the test, yet a lot of people miss it. You know why? Because they tend to overthink it. First, it says, given the following uniform distribution, and this works only for uniform distributions, answer the following questions. Now, first and foremost, why don't we count how many rectangles we have here? All right, I'll use a red pen. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 rectangles. Because there are 12 rectangles, watch this. All 4 answers are going to be out of 12. Without me even thinking about it, it's out of 12. That's it. So it says in part A, what's the probability of me throwing a dart at the board right here and it landing anywhere between 4.93 and 5.03? Let me use a highlighter pen for this. Let's just count up the number of rectangles from 4.93 to 5.03. And by the way, I noticed I didn't draw my histogram the way we have been with the numbers in the centers of the rectangles, but for the purposes of this example and the fact that it's a uniform distribution, I did it like this. So from 4.93, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. So that's going to be 10 rectangles out of 12, 10 12ths, I'm done. That's it. That's all you need to do on the next particular test. How about from 4.90 to 5.03 in part B? First off, are there any weights here in grams? And by the way, let's just say that this is the weight of some small object, and let's just say that this weight represents grams. And it's important that we're talking about the weight of an object here because of the type of variable that weight is. We'll get to that in a second. But are there any weights here that even go as low as 4.90? No. So 4.90 is a moot point. All right. The lightest weight is 4.92. Let's call it grams. All right. Let me use a different color highlighter now. Let's use purple. Okay. Actually, did it change? There we go. Is it going to change? Oh, might not change. All right. Well, if it doesn't change, let me just do it down here then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 weights from 4.92 to 5.03. So that's 11 out of 12. Done there. Okay. Last 2 questions and we're done. Less than or equal to 4.96. No, less than or equal to 4.96 let me use the moon pen for this. Wouldn't that just be here, 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 and here? That's exactly what it would be. That would be 4 rectangles out of 12. Then we come to the last question. What's the probability of being less than 4.96? What's the only difference between C and D? The only difference between C and D, all right, and I'll even write that right here. Difference between C and D is essentially the equal sign, the probability of X being equal to 4.96. So if we can find this probability, we could state the difference between letter C and letter D. However, let's think about the fact that we were measuring weight here. 4.96 grams is one particular weight, but it's one particular weight out of how many total weights? I mean, forget about the fact that we're going from 4.92 grams up to 5.04 grams. What about just between 4.96 grams and 4.97 grams? How many weights are between 4.96 and 4.97 grams? Can you even count the number of weights? Remember, you don't count weight, you measure weight. That's because weight is a continuous random variable. And because weight is a continuous random variable, we measure it on an infinite scale. So it's one weight, technically, out of an infinite number of weights between 4.92 grams and 5.04. And 1 divided by infinity is such a small number, it is essentially 0. We're talking about limits in calculus right now. So if the probability of being equal to any one given weight here is 0, is there a difference between C and D? The answer, my friends, is no. And the answer is no, simply, and this is the most important, simply because we're dealing with a continuous random variable. When dealing with continuous random variables, there is no difference between less than, or equal to. So with that said, I am now going to just talk about the homework with you. Keep in mind that this example with uniform distribution and weights deals with a continuous random variable. However, when you are doing your homework tonight, okay, number 95 is a simulation with numbers from 5,001 to 10,000 inclusive. This word inclusive is huge. Inclusive means you include the 5,001 and you include the 10,000. You know what that means? How many numbers are between 5,001 and 10,000? There are 5,000 numbers. So all of my answers for A, B, C, D, and E are going to be out of 5,000. I don't know if you're going to see that glitch on the video like I do, but it's glitching every single time. And why is this different? It's because number 95 deals with discrete data. So how many numbers are less than 3,000? I'll just do one with you. Wait, are there any numbers less than 3,000? You're beginning at 5,001. No, so there are 0 numbers less than 3,000. Greater than 8,000. So wait a second, we're talking about discrete data. If it's greater than 8,000, you don't include 8,000. So technically, you're beginning at 8,001 and you're going up to 10,000. How many numbers are between 8,001 and 10,000? I'll give you a hint. It's not 1,999. It's 2,000 numbers, everybody. Why? Well, count your way just from 1 to 10. How many numbers are from 1 to 10? Not 9, but 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because you're counting the bottom number and the top number. That's the importance of saying the word inclusive. Okay? I want you to treat number 96 like it is continuous data. Even though it's money and money gets rounded to the nearest penny, I want you to treat it like it's continuous data. And then definitely number 100. Pollution levels are definitely, pardon me, continuous data. So treat those like continuous data. That's it. Bye, everybody.